Everything you touch and use in your day-to-day life, from power, plastics to petrol, starts here in a refinery. It's the beating heart of modern civilization, but it's running on legacy tools. Operators are overwhelmed, decisions are delayed, millions are at stake. What if AI could understand your plan, speak to your machines, and speak to you like a seasoned engineer? Orbital doesn't wait for a report. It thinks, it explains, it recommends instantly. No dashboards, no waiting, just action. Orbital, built for the front line.
Cool. I'll now talk to you why and how we came across building Orbital, because this wasn't just something we concocted overnight. It was a regular monthly and yearly study to really understand how current users work in their workflow in refineries, in the control room, at the front line, in order to design a product that works for them. So before I dive in, a brief intro to me. I'm Sam Tukra, the co-founder and chief AI officer of Applied Computing. And prior to Applied Computing, I did my PhD in AI and autonomous robotics at Imperial College London. And then for the past several years, I've been developing autonomous systems for heavy industry, more recently at Shell, where I was part of some of the most ambitious AI deployments across their refineries globally. And one of the biggest opportunities I had was not to just work in a lab, but be in the front line and speak to the control engineers that are operating this very world Cal talked about. And one thing that remained a constant, no matter what we tried to push out, was nothing ever stuck. So today, I want to discuss 3 things that I want you to get out of this talk. First, we're going to get to the bottom of answering why is it that AI has failed to transform this industry thus far. Second, we're going to talk about the economic value of the actual transformation itself and, well, what Orbital can achieve and the importance of it. And third, you all should be able to run a refinery by the end of this. That is the aim. So it is no doubt to anyone here that we live in a world where, AI can beat grandmasters at chess or write symphonies, and including being able to fly and drive autonomous vehicles. Yet, in the industry where millions of dollars move with every valve turn, nothing had changed. And we were flabbergasted when we actually initiated on this idea when I called Cal. It's like, we have to start working on this problem because it doesn't make sense to me whilst we were there. And we decided to really understand what are the products that are currently offered from the market in this particular industry to get to the bottom of answering that very question. Why has transformation not taken place yet? And upon digging deeper, we found the majority of the products right now operate in what is known in the industry as safe zones, which are stuff like inspection or anomaly detection, things that are low risk and don't really drive a critical impact or any operation that has a direct transformation to the economic impact and the bottom line. And this isn't just 1 or 2 products, it's actually most of the sector today. If you think about it, even if I was to deploy an inspection algorithm, and if I was to miss an inspection, regulatory approval will require manual inspection to be taken place anyway. So at best, you save a few hours for a manual operator to go around and change those actual items that you're inspecting. These are fundamentally not targeting the decision-making process with an economic value attached to it. And what we realize is that to truly transform operations in heavy industry, for the intents and purposes of this talk, we're going to stick with refinery because refineries are awesome. In order to truly transform them, AI needs to step into the heart of decision-making so that there is a direct economic value tied to it, so that we can measure impact for this industry. Otherwise, it will always be a variable. And in order to trace that line, what we realized is, upon months of interviews and actually physically visiting them in gorging heat in India as well as Europe, the decision-making happens directly in the control room. But the control room never left the 90s. Despite all of the transformations we've had in the internet world with technology, the control room only updated their monitors to be HD and their chairs, but the entire operations were still the same. And this was very confusing to us and also exciting because this provided the opportunity to change. So we decided to understand as a team, let's really get to the bottom of what they're dealing with. Why is it that nothing has changed? So let's dive into that. So what a refinery, I don't know, before I dive into that, how many of you actually know about refineries or have been and visited to one? I'm just curious. Okay, wow, decent amount, cool. So the awesome part of refineries is it's hella complex. We're talking about 15,000 different pieces of equipment that are communicating with one another in real-time intervals. And that data from sensors are transmitted at every 1-minute intervals directly to the control room. And a control room is usually about 20 to 30 people, supported by other engineers that are in the background, usually away from the refinery or some within the refinery. But the decision holding from the lead operation of what happens in the front line centers at the focal point of the control room. And that's the complexity they're dealing with. And the cool thing is, when you start to understand what are the numbers that they're actually handling in terms of the economic value of their decisions, usually refineries are measured by their capacity of the number of barrels per day they process. So a mid-tier refinery would be about 200,000 barrels per day of crude that they process and get a final product. So in today's margins, that would be about $8.37 they would make from each barrel processed in total. And that gross margin blows up to $610 million. Now, $610 million sounds like a huge number, but refineries don't run cheap. Refineries are super expensive to run and maintain. In fact, 45% of that will almost go just to use the energy to run every single operation in a refinery. So take about 200 million out of that margin right there for energy. Take about additional 10% for running costs, such as maintenance, so about 50 million. Another 8% for maintaining turnaround, so around 40 million. And then there's also staffing. Let's add another 30 million to the mix. Oh, and debts and taxes, right? So let's add another 30 million to that. And every time you get to the bottom of all of the expenses of running a refinery, for this same mid-tier refinery, what you're left with is about 60 to 80 million dollar in free cash that you get to keep in your pocket. But it doesn't stop there, because every year you have what is known as money leaks, unplanned cases that occur every year. Unplanned downtime for a few days, almost a single day could jump from 350K to almost $1 million. You also have wasted energy, where at times equipment strains and you have to burn more energy in order to get the same product. And so on. Maintenance ad hoc, missed optimization opportunity, which creates the product that you don't need, and then you have to recycle, get rid of it, and you can't sell it, so your buyer is no longer happy with it, etc. Right? So total, this same mid-tier refinery would leak about average $50 million that year. So you can see the importance of clawing back every cent in order to make sure that these leaks don't occur, so that your actual free cash left at the end still holds value. And a small change moves this number really fast, right? Such as trimming energy or even optimizing to make your product spec better, etc. And the cool thing is that, well, it's not really cool, but these numbers, when you extend it to almost 450 refineries that exist on Earth today, that's about $45 billion just left on the table of these money leaks, right, annually. That is the opportunity for Orbital and AI in general to be able to prevent these money leaks through cutting down time to a significant low, optimizing your operations so that you can get the most out of every energy and every cent that you actually utilize. But this is only one half side of the story. Because when you do make those changes, when you do make your operations more efficient, you start to increase throughput. And that's when you have the ability to make more money. And that number is the most exciting because we don't know what that number really is. If we start to actually utilize most of AI for optimizing our processes, even by adding 50 cents to that dollar margin, to that barrel, which is about 4 to 5% extra, you unlock $15 billion of pure EBITDA that wouldn't have existed by increasing throughput. So there's two things that refineries have to control: reduce the money leaks and increase throughput. That's the opportunities they're looking for, whilst maintaining and firefighting to ensure the leaks remain at a minimum. But they haven't changed. So the opportunity is actually far bigger than we think from just reducing money leaks, but to actually open new avenues of throughput. So what happens in control room today in order to try and achieve that? All the data from all of those equipments, all of that real-time information is rerouted to something known as a DCS, which is a distributed control system. Think of it like, in hacker movies, they say the mainframe. You ever heard that term? Yes. It's that, right? It's just that mainframe where all the data comes to. And you have these amazing monitors that you can see every single trend, including the process flow itself. And on those, they run optimization algorithms, which are basically statistical algorithms taken from textbook physics, typically known as first principles, first order physics equations that define how the process actually runs inside these equipments. And using that, they start to measure variation as well as doing prediction and looking at changes and anomalies and make all of their decisions based on this. But these existed 40 years ago, and they still haven't changed because they're the most explainable to them. But the problem is they don't cater for all 100% of the data because at the end of the day, they're static physical equations. They don't adapt to live changes that are happening in a plant, which is almost always, and therefore they also lose out on the precision needed in order to get and unlock those throughput margins or plug those leaks. So at this point, when we understood how they actually run and what equipment they use, we got even more frustrated because the first thing that came to our heads was, if you're now doing statistical optimizations, why not just AI? Because at the end of the day, that's what they're known for. They're universal function approximators. Deep learning can indeed open the doors here. So why is that not being used? And there was just one line the control room operator said that sort of answered it all for us, which was the fact they don't trust a black box. Today's deep learning, although has shown immense value in the internet world, it's still in a world where consequences are not real. Here, if deep learning, if we look at it today in terms of what the algorithm does, it predicts, but it doesn't explain why or what is the context for that predicted number. It's just the next token numerical figure. And for people that are in the control room, these engineers, they can't trust an output. They can't explain why. And for them, it's super important because being able to explain why take a certain actions drives the consequences you get when you're wrong. For example, cities suffer, people die. Texas City explosion, 2006, 20 dead, $322 million loss, 180 fatally injured. Not to mention the countless downtime that also occurred. Deepwater Horizon. No life will ever exist on that 480-kilometer seabed of that contamination. $65 billion loss, biggest known to history in oil and gas sector. These are very real consequences of certain decisions made. They are vivid, tragic memories. And the thing is, every year, at every scale, every refinery has certain consequences they have to deal with that lead to downtime, that lead to changes every year. Sure, the big ones make it to the newspapers, but even the small ones can drive a huge dent in a refinery's bottom line. In fact, the year I was joining Shell, before that, Shell had a mini explosion in Moerdijk. to which they were brought to court. And although what was reported was a 2.4 million euro fine, but if deep in the text, what we saw was there was a 12-day downtime, which was a $15.6 million hit. Now that's a huge chunk of the free cash left at the end of all the expenses that they took a hit on. So, control room, they deal with high risk because every decision has an impact directly at the bottom line and has a dollar value. But there's also high reward because once you do optimize, once you do increase those throughput or yield, and when you do plug in those leaks, the change is transformational. And for our engineers that are in the control room, they need to be able to explain their decisions because no black box will ever be worth a gamble to run their operations with. And that's why the answer to that question, why AI has failed to transform this industry, truly came down to the fact that we never developed AI with trust as a central point within the algorithm. We only made sure that the predictions were high precision, but trust is not optional in the real world space. It has to be foundational so that we can explain every decision and answer that why, followed by what. And therefore, after realizing this, what you see in the market today, two worlds exist. One that's run with deep learning and AI that is super accurate and fast, but it's not trusted, so it's used on low impact and low risk problems. And the other, which is purely based on physics, because it can be explained, but unfortunately lacks that same level of precision and unlock to that value. So my research team and my engineering team, who some of people are actually here, so I do recommend talking to them afterwards as well. What we decided to do was really just say, what if we can merge the two worlds together and find a way to have a dedicated AI agent that focuses on explainability so that we can unlock that trust? Because when you see that world, those reasoning of every prediction being presented to the user in a manner that is understood and well-versed in the world of physics, grounded to that reality, trust unlocks itself. And we designed it so that these three independent minds would work together in order to learn trust with every usage, with every use of Orbital itself. And the beauty is, when this has been implemented as human intelligence, like literally us humans working together with data, being able to explain every prediction and every recommendation with that precision of machine learning used by side, we have seen immense value. For example, Shell increased production 1.58% in LNG. That was a $30 million win for them. Same thing with deferring production because of faulty equipment that was detected beforehand, $15.6 million saved. This was done by 26 people, just a team dedicated for an entire year making data-backed decisions with machine learning. Same thing with Equinor, right? 4% increase in production, $27 million banked. But if we achieve this performance, not months, but every second in the form of an algorithm that processes all of that data in real time and explains the reasoning consistently, continuously, and accurately. Oh wait, it says safely too. And safely, that's when you start to transform the industry. So before I continue becoming a barrier to you at lunch, I want you to remember out of this talk, trust can't just be a feature in AI for the real world. It has to be the very foundation, and it has to be designed with explainability in mind. So for AI to transform this industry, trust is the foundation. And the second thing is that any small improvement in these operations, given the scale and vastness of it, it changes that economic value fast. And the true unlock is the opportunity that we are, well, going to see in the future very, very soon.